Last time we saw indeterminate forms and using L'Hopital's rule to find limits when those limits are in indeterminate form using some derivatives. This time we're going to see how we can expand that power by looking at other kinds of limits that it's not clear how to plug into them, like infinity minus infinity, or weird ones like 0 to the 0, because that base 0 wants it to go to 0, but that 0 in the exponent wants it to go to 1. So there's lots of these other kinds of forms that it's unclear how to plug into them, or it really depends on the different rates of change of the parts involved. And so we want to see how we can turn these forms into fractions that might be an indeterminate form so that we can then use L'Hopital's rule. Do a little bit of algebra first, then do the calculus. So for instance, if we had a difference, really in this infinity minus infinity case, cosecant minus cotangent as x goes to 0. This might not be totally obvious to you at first, but let's go ahead and expand this out, maybe to help you out. Cosecant is 1 over sine of x minus cotangent is going to be cosine of x over sine of x. So looking at that, it becomes a little bit more clear that this whole first fraction is going to infinity, right? 1 over 0. And this whole fraction is also going to infinity because it's going to a 1 over 0 situation. All right. I don't really know what that is. Infinity minus infinity doesn't make a lot of sense. It's really going to depend which of those is growing faster. Is one of them going to dominate the other? So I still can't use L'Hopital's rule, but I can try to put these things over a common denominator. So let's go ahead and do that. This is going to be the limit as x goes to 0. Oh, they're actually already over a common denominator. Super nice. 1 minus cosine of x over sine of x. Now this looks like, if I plug in a 0, I get 1 minus 1. This whole thing is going to 0. This whole thing on the bottom is also going to 0, which means I can use L'Hopital's rule. Do your reader a favor. Include that LR. Hey, I'm about to take some derivatives, otherwise it can be quite shocking to see everything change so much. The derivative of the top, not the quotient rule, but just the derivative of the top, is going to be 0 minus negative sign, so sine, over the derivative of the bottom is cosine. Oh, this is like what we wish the quotient rule was. Nice. So now if we plug in, the top is going to 0 and the bottom is going to 1. I like that a lot. This whole thing is just going to be 0. Great. Do check every single time. Sometimes people just want to keep using L'Hopital's rule, and in this case, it's not indeterminate. In fact, it's just 0. Okay, so basic idea is with a difference, see if you can either factor or find a common denominator are the two main things you're going to do to either simplify it or turn it into an indeterminate form. Okay, next up, what if we are multiplying? This is a classic example. X versus natural log of x. X times natural log of x. What is happening here as x goes to 0 is this x is going to 0, but this natural log is going to negative infinity. And the question is who's going to win? That x wants it to be small, and that natural log wants it to be really big and negative. So I need to find a way to rewrite this thing. So algebra step, not even a calculus step, says let's write this as a fraction. If only there was a good way of writing it as a fraction. Here is our trick. Not even really a trick. If I want that x to be in the denominator, I need its reciprocal. I'm just going to take it to the negative 1. So that was just a little algebra. To move something to the denominator, just take the reciprocal or take it to the negative 1, and now I can flip or put it in the bottom. This looks like a fraction. In fact, not just any fraction. This is going to negative infinity. This, x to the negative 1, as x goes to 0, remember x to the negative 1 is just 1 over x. This is going to positive infinity. This is now indeterminate. I can do my old friend L'Hopital. Okay, you'll probably see this coming up on homework and other types of problems. This is a really common thing to notice, is that, oh yeah, I can turn products into fractions by just taking a reciprocal or taking to the negative 1, and then I can use L'Hopital's rule. So let's do it. Derivative of natural log, 1 over x. I highly recommend parentheses, otherwise these compound fractions look mighty nasty. Minus x to the negative 2. Whew, looks kind of messy. Your job now is to simplify like crazy. See if I need to do another L'Hopital's rule or if I can clean it all the way up from here. So this is now an algebra issue. This is the limit as x goes to 0 from the right. In fact, let's even do a little scratch work on the side here. 1 over x over negative x to the negative 2 is equal to, well, that negative can hang out front. That negative x squared means it can flip to the top, but that 1 over x means it can move to the bottom. So both of those flip sides, this crosses out with that. I'm just left with that negative x. Okay, so that might have taken you a little longer. Make sure you can do that simplification, that compound fraction work. It's bound to come up again. So this is just a negative x. Well, what happens to negative x as x goes to 0? That's a 0. Okay, oftentimes if you need to move something into the denominator, you're going to end up with these compound fractions as you work your way back into a more simplified form at the end. It's kind of the price you pay. Cool. So that's how we deal with products. What about with powers? I'm super curious if you actually know what this is. The limit as n goes to infinity as of 1 plus 1 over n to the n. This is a very famous limit. I'll talk about why in a second and why I'm using n's. Okay, so inside of here, everything is going to, well, 1 over n is going to 0. So this is going to go to 1. But my power is going to infinity. So I'm getting smaller and smaller numbers on the inside while I get bigger and bigger numbers in my power, in my exponent, and they're going to fight it out. And we'll see what happens. This is going to require a little bit of more work. You might know that we have this general strategy for dealing with exponents that seems to work all the time, and it's going to work here as well. Whatever this thing is, let's just call it y. And I want to simplify that exponent, so I'm going to take the natural log of both sides. This is how we deal with exponents so often in math. So if I take the natural log of both sides, I get this limit as n goes to infinity of the natural log of 1 plus 1 over n. And now that using my power rule, that n comes in front. So it's no longer an exponent, it's now a product. Super nice. You should ask yourself, am I allowed to bring the natural log inside of my limit? And we kind of brushed over it, but yeah, my log rules say I can. Natural log behaves really, really nicely. And if that limit exists, the natural log of that limit exists, and I should be able to bring it inside. Okay. There is a little bit of a question of if I have positive or negative numbers. These are always positive. We could have done absolute value of natural log if we wanted to. Okay, nice. Now what? Well, now we just worry about this limit on the right. And we need to play the same game as before. We have a product. This product looks like I have infinity times natural log of 1. Natural log of 1 is just 0. Okay, so I'm in this fun place again. Let's work our way through. Oh no, I messed up my color palette. That's okay. I'm going to focus on this limit by rewriting it as a fraction. Do you know how? I'm going to keep that natural log on top, much cleaner that way, and then n to the negative 1. This looks really familiar. Let's do this L'Hopital's rule again. Now that, by the way, I should check. This is going to, looks like 0, and this is going to 0. So my L'Hopital's rule can be used. I'm going to get a careful, actually I'll give myself a little more space. This top derivative is a bit more complicated. Give it a try. Natural log of stuff, so I'm going to get 1 over all that stuff. And then I need to multiply by the derivative of that stuff. The derivative of 1 over n to the negative 1, its derivative is going to be negative n to the negative 2. That's just my top. Whew. My bottom is going to be negative n to the negative 2. Oh my goodness, I lost my limit. I should probably include that as well. Limit as n goes to infinity. let's go ahead and do a little algebra, see if we can clean it up. Remember that everything with a negative exponent can flip sides, but also, by the way, it looks like these entire terms cancel. And the way our compound fractions work is that if you're in the denominator of one of these smaller fractions, you can also flip sides. So let's clean this up a little bit here. It looks like this entire term cancels with this entire term. This is really not so bad. So this whole thing is going to equal the limit as n goes to infinity of 1 over 1 plus 1 over n. Great. Now what happens? Well, this little 1 over n is going to 0. What am I left with? This whole thing is going to be a 1. Now, I'm not quite done. I'm pretty happy I got this nice 1, but remember what I just found was that natural log of my answer is equal to 1. So if I want to undo that natural log, I need to take e to both sides. So y is equal to e to the 1 is equal to e. That's it. So after we've solved for that y, this e is our amazing answer. Hopefully, maybe that's familiar. Oftentimes, this is the definition of e. This old limit right here, especially if you learn this using compound growth or continuously compounding rates of change, then this will be given to you as the definition of e. Saying, okay, as we compound or exponentiate more and more frequently, then you end up with something like this. So maybe this is familiar. This might have been how you learned what e was in the first place. Okay, let's do another power one that looks a little bit weird. And we'll start to wrap this up after that. Maybe give this one a try. It's the same method. I want to do another one because the method is a little longer. Y equals, I'm going to take the natural log of both sides. I can bring that natural log in. Natural log of x. When I do this, that exponent can come down. So you get x natural log of x. This looks super familiar as well. They do kind of start to look alike. We've actually already done this one. X natural log of x. I'm going to work through it again just for old time's sake, maybe at twice the speed. So this is equal to the limit as x goes to 0 from the right of natural log of x over x. That is now an indeterminate form. So I can take L'Hopital's rule. Do check every time that it is an indeterminate form. So this is going to look like 1 over x over, oops, sorry, there's a negative 1 there. X to the negative 1. I got to take that power to get it into my denominator. So this is now negative x to the negative 2. Lost my limit. Don't forget that. Okay, this simplifies a whole heck of a lot. So this becomes the limit as x to 0 from the right of negative x, doing that simplification from before, and this is going to equal 0. All right, went pretty fast because it was the same calculation as before, but now make sure that remember natural log of y is equal to 0, so y is equal to e to the 0. What's e to the 0? 1. Great. Kind of bizarre. This is a really weird function, x to the x, but its limit as x goes to 0 is 1. So in a very weird way, this x up here wins the battle, because this x wants it to go to 0, this x wants it to go to 1, and this one happens to win. So 1 is our answer there. Super cool. Okay, just a quick reminder while we're at it, it's always good to remind you that L'Hopital's rule is not always the right way to do things. So this rational expression here, you could do L'Hopital's rule 21 times to find out that the answer is 1. Or, don't forget, we have other methods. We can still multiply top and bottom by a power of x. In this case, that power should be 1 over x to the 21. 1 over x to the 21. And that's going to go much, much faster than L'Hopital's rule. Similarly, we've seen other cases where the right thing to do is to factor x squared minus x. Looks like infinity minus infinity, but the right thing to do here is to rewrite it in a factored form. And now it's quite clear that the answer is going to be infinity times infinity. That's going to be infinity. Okay, so L'Hopital's rule is not always the answer. You still need to remember our old tricks and tools from the past and using continuity to our advantage. But usually by the time people get a couple of problems under their belt, it starts to feel really nice and a little more satisfying than some of the other limit problems. So give it a try. Enjoy.